Today, I'm going to talk about the boundary conditions of the electromagnetic waves between two media. So, let's assume that there is an interface between media 1 and media 2. These material systems, they are characterized by their electric permittivity, magnetic permeability, and the conductivity, respectively. Let's do the electric flux first. Let's assume that the electric flux density is pointing from media 2 to media 1. This is media 2, this is media 1. This is electric flux density. So to derive the boundary conditions here, we first recall the Maxwell equations, the Gauss law. That is, the divergence of the electric flux density is equal to the charge density. So, what does this divergence mean? That means the limit of infinitesimal volume and the integral of a closed surface of the electric flux density over ds. Okay, so this we can apply the Gauss theorem. This part is equal to the integral of the charge density, which is equal to Q, the charge. Now, back to this interface problem. So how to do this integral of the electric flux density? Note that we have a two media, so we can define the integration root. We can use a Q box, looks like this. This is a cylinder with h as the height of the cylinder. Now, back to this. This is a closed surface. Now we use this as a closed surface to do this integral. And we define this as d as 1. This is d as 2. And d as 2, if we use a vector form, this is equal to, if we define a normal direction of a unit vector here, then ds2 is equal to an ds. This is scalar. For here, we also use an2. AN1 equal to AN1 and ds. These two ds have the same magnitude, but these two vectors are opposite. Now here, this part is equal to, first we do the integral of this surface, that is S1 d1 dot product ds1 plus S2 d2 dot product ds2, and the side wall of the cylinder, if we take the limit of h, if it is 0, infinitesimally small, then we can say that the contributions of the electric flux density across the surface of the sidewall is 0. So we only need to take this 2, and this is equal to the charge. Now we don't use charge here. If we have a charge density, surface charge density of this interface, denoted as low s, then we can write it as low s and ds. The dot product here is a scalar form, so we can use a scalar form here. Now, we can make a simplification of this vector and this vector. Look at this. We know that the AN1, AN2, they are of the opposite direction. That means we can write it as a scalar form. D1 AN1 ds S2 D2 AN2 ds equals rho s ds. What does this mean? This is the projection of the D1 onto the direction, this direction. So we can use dn1 to denote this part. That means if we have d1 in this direction, this is an1 direction, unit vector. That is the projection. This part we call dn1. Okay. So we can simplify it as dn1. This is dn2 magnitude. And these two unit vectors, they are of opposite directions. So here is minus dn1 minus dn2 is equal to rho s. So now we get the first boundary conditions. I write it here. First boundary conditions is dn2 minus dn1 equals surface charge density. This is for general boundary conditions. Let's go on. For the magnetic flux density, B, we apply the same rule. This is very similar to the electric flux density. So, divergence of B, so according to Gauss law, is 0. That means there is no magnetic monopole. So if we also use a pure box, similar, very similar to the first one of A and 1, A and 2. This is B1, this is B2. So it is very similar. We do the surface integral of B ds according to Gauss law of magnetics. It is 0. This part is equal to, back to here, S1 P1 AN1 ds S2 B2 AN2 ds, and this is equal to the projection of this part on the normal directions. That is Bm1 minus Bn2 is 0. So back to here, we get the second boundary conditions. That is Bn1 is equal to Bn2. So let's go on. Now we have derived the boundary conditions of the electric flux density and magnetic flux density. So what about the boundary conditions for electric field intensity and magnetic field intensity? So electric field intensity as E across these two media. So first we recall from the Maxwell equations, the Faraday's law. The Kerr operation of the electric field intensity is equal to the rate of change of magnetic flux intensity. So firstly, the definition of the Kerr is the limit of infinitesimally small surface, and here is the circulation of the electric field intensity, and we take the maximum value of this circulation and have the direction of this unit vector direction. Now we can use the Stokes theorem that the circulation of the electric field intensity equals to the surface integral of this curl operator. So this equals this part B ds. So here we take this differential part outside the integral because that this part is only dependent on the positions, not the time. Okay, so in this two media system, we are not going to use a pill box to solve. We are going to use a loop because it is a circulation. So we have, in this loop, we have infinitesimally small length, contour length, we call it dl. So this part, you can call it dl1 vector. This part, dl2. It is circulating in this direction. So we also define the height of this part is h. Okay, so back to here, this circulation is equals to L E1 dl1 plus L E2 dl2, and this equals to this part. Now, something interesting is that if we also take the, because this is infinitesimally small, so if we take the limit of h when it is approaching 0, then it means the integral, look at here, the contribution of the magnetic flux density, the contribution of this to, note that this is a surface. That means if h approaches 0, the contribution of the magnetic flux density across this surface will be 0. The contribution of this part vanish. Okay, so note that these two vectors are of the opposite directions. So now look at this. This is E1. This is dl1. The dot product means the projection of this E onto this dl1. So this part we call it the tangential component of electric field intensity. We call it ET1. So this part is equal to ET1, and this part is equal to ET2. These are opposite directions, so minus. Now we get the third boundary conditions. We can summarize it on here. ET1 equals ET2. That means the tangential component of the electric field intensity is ET1. ET2 equals ET1. Now, let's go on to find the last boundary conditions. That is the magnetic field intensity H. So similarly, we can write the curve of H according to the Mps Rule and also Maxwell equations is equal to the conduction current density and rate of change of electric flux density. If we use the Stokes theorem, that is circulation of the H, equals surface integral at J and surface integral of electric flux density. Okay, similarly, we use a closed loop to solve this part. Similarly, we can write it as HT1 minus HT2. Okay. Instead of using this part to derive the boundary conditions, we directly look at the Mps Rule. That is the circulation of the flux, magnetic flux density equals the current enclosed. So here, what is the current enclosed here? Now, I should firstly tell you about what is a surface current density first. If we have a surface called S, and there is an infinitesimally small contour line, we call it delta L, and there is a current delta I across this contour line in the direction of AN. And then we can define that the surface current density is equal to the limit of L approach 0. I in the direction of AN or A max. We note that this AN, this vector also lie in the same plane of the surface and normal to the contour line. So from this we can define that the current is equal to the integral of the surface current density in the direction of AN dl. No. Or we can say that this is dl. Now, what is the unit of the current surface current density? from here we can easily observe that the unit should be amps per meter. Now we have these equations. Back to we apply this to here. The enclosed current, let's assume that the surface current is flowing in the direction into and out of the paper directions, and also normal to the loop and normal to this flux, to this field intensity. So the enclosed current, we use these equations. That is line integral. You have line integral here. Line integral equals surface current density. This is the surface current density in these directions, or these directions, dl. This should be, we observe that we have already used scalar here, so this should be in a normal directions. What does this mean? This means exactly in these directions. Then we can say that we cancel this and we get the HT1 minus HT2 should equals surface current density in these directions. Okay, so when should we apply this? This applies when there is free charges on the interface, and the moving free charges result in a current. If there is no free charge at the interface, then we can say that HT1 also equals HT2. And this happens for two perfect dielectric media where no free charge exists. But now we are doing a general form of the boundary conditions, so we can summarize here that the HT1 minus HT2 should be surface current density in these directions. HT1, HT2, and surface current density. If here, we can say charge density. Okay, now we have derived a complete boundary conditions, a general form for an interface between two material systems.